Good morning, everyone. Welcome. In our session today, we're going to make a really important shift. We're moving away from the abstract theories we've been discussing and diving headfirst into a practical, fundamental tool for strategic business analysis. We're going to explore a concept from calculus that, believe it or not, has direct, incredibly powerful applications in the boardroom, out on the factory floor, and really in any role where you are tasked with making smart financial decisions.
So let's start with a core question. This is a problem that every single operations manager, really every business leader, is going to wrestle with. It's a question that lives right at the heart of operational strategy. Now, on the surface, it seems pretty simple, but the answer, well, it's rarely straightforward. Think about it. Producing more units might boost your total revenue, and maybe even your total profit. But is the cost per unit going up or down? Are you actually getting those economies of scale you hear so much about, where producing more makes you more efficient? Or are you hitting what we call diseconomies of scale? Those hidden inefficiencies that start to creep in as you grow, like supply chain bottlenecks or increased waste. Answering that question takes a lot more than just basic arithmetic.
So here's our roadmap for today. We're going to start by digging deeper into the why, this whole efficiency question. Once we get that, then we'll tackle the how, the specific math tool we need to solve it. From there, we'll apply this tool to a realistic business scenario, walk through the math step by step, talk about some common mistakes I see all the time, and then, most importantly, we'll translate our math findings back into something you can actually use, real business intelligence.
To really answer that opening question about efficiency, we just can't look at static numbers. A single report, the average cost at the end of the quarter, it's just a snapshot in time. It's not enough to plan your strategy. What we really need to understand is the rate of change. We need to know the trajectory of our costs. Is our average cost getting better or worse as we go from making the 100th unit to the 101st, or from the 1000th to the 1001st? It's this dynamic, marginal way of thinking that really separates basic bookkeeping from true strategic financial analysis. That ratio, cost per unit, is what we call the average cost. And by definition, it's a fraction, right? It's your total cost function divided by the number of units you produce. Now, in mathematics, anytime we need to analyze the instantaneous rate of change of, well, pretty much anything, but especially a fraction or a ratio, we turn to our calculus toolkit. And this is exactly where the process of differentiation, the act of finding a derivative, becomes an absolutely essential tool for any business leader who wants to make smart, data-driven decisions.
All right, so let's pull back the curtain on the specific tool we're going to use. It's called the Quotient Rule. And the name itself gives you a big clue. A quotient is just the answer to a division problem. So this rule is designed specifically to find the derivative, that instantaneous rate of change, of a function that's set up as one thing divided by another. That's exactly the situation we have with our average cost function.
Now, I know what you're thinking. A formula like this can look a little intense at first glance, but our goal here is to get the logic behind it, not just to memorize a string of letters. Let's think of g of x as our function on top, the numerator. In our business case, that's going to be our total cost. And we'll think of h of x as our function on the bottom, the denominator, which will be the number of units, x. What this formula really tells us is exactly how to combine these functions, and this is the critical part, their own individual rates of change, g prime of x and h prime of x, to find the overall rate of change for the entire ratio.
To make this formula way more manageable and, honestly, to keep from making silly mistakes, we use a little shorthand, which you can see laid out in this table. We call the numerator function, g of x, the high part, and the denominator, h of x, we call the low part. So it follows that their derivatives, g prime of x and h prime of x, become d high and d low. By breaking the problem down into these four distinct pieces, any complex-looking ratio becomes a lot easier to handle. Our job just becomes identifying these four parts correctly before we try to put the puzzle together.
And here's a simple mnemonic that I really want you to commit to memory. Seriously, it will save you from so many headaches. It goes like this: low d high minus high d low over the square of what's below. Let's just say that together. Low d high minus high d low over the square of what's below. See? This little rhyme perfectly lays out the entire formula for you. H of x times g prime of x minus g of x times h prime of x, all of it divided by h of x squared. And make sure you get that subtraction in the right order, which, trust me, is the #1 place where people mess this up. Okay, let's move on and see how this all clicks into place in a real-world scenario. Let's apply this to a situation that you will absolutely 100% face in your careers: analyzing production costs. All this theory is great, but it's only valuable if it can solve real problems. So let's ground this concept in a real business case.
I want you to really imagine this. This is your job. The CEO walks into your office. She says, "We're planning to double production next quarter. From an operational view, is that a good idea? Are we going to get more efficient or less?" Your job is to give a clear, data-backed answer. You've got to figure out if the cost per drone is going up or down as you scale up. I mean, your professional credibility and the company's bottom line are riding on you getting this right.
So your accounting department hands you this, the total cost function C of X. Here, X is just the number of drones you produce. Let's take a second to really break this down, because understanding these pieces is key. That $1,500, that's your fixed costs. Think of it as the rent on the factory, the lights, salaries, stuff you have to pay for even if you don't make a single drone. The 10x term, that's your linear variable costs. For every drone you make, it costs an extra $10 in materials and labor. Now this last term, the 0.02x squared, this is the really interesting part. This quadratic term represents costs that go up at an accelerating rate as you produce more. This could be things like overtime pay, extra wear and tear on machines, or maybe the factory just gets more crowded and less efficient. This makes it a very realistic and nuanced model.
Okay, so to get to the number the CEO actually wants, the cost per drone, we have to calculate the average cost. And we do that by creating a ratio. We take that entire total cost function, C of X, and we divide it by the number of units, X. And this gives us our average cost function, AC of X. And as you can see, plain as day, this function is a quotient. It's one function divided by another. This makes it the perfect textbook case for using the quotient rule we've just been talking about.
So let's walk through the calculation together, step by step, just like you would if you were prepping for that big meeting with the CEO. We're going to take our average cost function, apply the quotient rule, and find its derivative. That derivative is going to tell us the rate of change of our production efficiency.
Okay, first, we just methodically lay out our four pieces. The high part, g of x, is the whole numerator, our total cost function, 1,500 plus 10x plus 0.02x squared. The low part, h of x, is just the denominator, x. Simple enough. Next, we find their derivatives. For d high, we just use the power rule. The derivative of a constant, like 1,500, is 0. The derivative of 10x is 10. And for 0.02x squared, we bring the 2 down, multiply it by 0.02, which gives us 0.04x. So d high is 10 plus 0.04x. And finally, d low. The derivative of x is just 1. Getting this prep work done right is absolutely key to getting the right answer in the end.
Now we just assemble the puzzle using our mnemonic. Remember, low d high becomes x times our d high function, 10 plus 0.04x. From that, we subtract high d low, which is our whole high function, 1,500 plus 10x plus 0.02x squared times 1. And all of that goes over the square of what's below, which is just x squared. Now, if you do the algebra carefully, you distribute the x and combine your terms, you get to the final derivative. AC prime of x equals 0.02x squared minus 1,500 divided by x squared. This new function, this is our analytical tool. If we plug in a production level, say 500 drones, into this AC prime of x function, the number we get tells us the exact rate our average cost is changing at that moment. A negative result, we're getting more efficient. A positive result, we're getting less efficient.
Before we get to the big takeaway, I want to pause here. This is incredibly important. I want to talk about a common mistake, a conceptual error I see all the time. And understanding why it's wrong is just as important as knowing the right way to do it. The reason this matters so much is that in business, a little calculation error that comes from a misunderstanding can lead to a multi-million-dollar strategic blunder.
So here's the trap. It's really common to see a fraction and think, oh, I'll just take the derivative of the top and divide it by the derivative of the bottom. It seems logical, but it is completely, fundamentally wrong, and it will give you a totally garbage answer. This is the perfect example of why following the right procedure isn't just about getting points on an exam, it's about protecting your company's money. In our drone example, taking this shortcut would give you a wildly incorrect picture of your efficiency, and you might tell the CEO to ramp up production right when you're about to fall off an efficiency cliff.
Okay, so let's bring this all home. What's the big managerial takeaway here? We've done the calculus, sure, but the goal isn't just to get a number. The goal is to translate that number back into a language that the C-suite understands, a language they can act on.
This derivative, this AC prime of x, it's not just some abstract number. It's a powerful strategic indicator. When AC prime of x is negative, it's telling you that making one more unit will decrease your average cost. You're in a good spot. You're on the right side of the efficiency curve. But when AC prime of x is positive, the opposite is true. Making one more drone will actually increase your average cost.
That's a red flag that inefficiencies are creeping in. And this insight is what drives critical decisions about pricing, about when to scale production, and when to invest in new equipment. Essentially, by analyzing this derivative, you can find the operational sweet spot, the level of production where your average cost is at its absolute lowest and your efficiency is at its peak.
And that's really the bottom line. Mastering this concept lets you go from just reporting numbers to actually interpreting what they mean for the future health of the whole company. It lets you walk into that CEO's office with confidence and say, look, based on my analysis of our marginal efficiency, I can tell you that we are currently getting more efficient with each drone we produce. I recommend we increase production. However, my model also shows that if we push past a certain point, that trend will reverse and our cost per unit will start to rise. At that point, we'll need to reevaluate. That is the real power of applying calculus to business. And I want you to remember that as you continue your studies.